This material is not in your textbook. It's actually not in the textbook that was used prior to the one that I chose for this class and all that kind of good stuff either. As I talked about it before, it's an integral part of making a semiconductor-based device actually function, because if you don't have a metal contact by which to apply a signal, you can't actually use your chunk of semiconductor for anything. As a point of fact, the metal semiconductor junction is the oldest form of semiconductor device. So metal semiconductor junctions were invented before semiconductor, or PN junctions were invented. And should be in the Smithsonian, I believe, Jack Kilby's first integrated circuit that was ever designed back when the rest of TI was on vacation effectively, and he was a new hire and didn't get to go, is made completely out of metal semiconductor junctions. I think that's out in the Smithsonian, actually. So a metal semiconductor junction occurs whenever a metal is deposited on a semiconductor material, which kind of makes sense. It's an interface between crystalline metal and crystalline semiconductor. One fundamental difference between metal semiconductor junctions and PN junctions is that a metal semiconductor junction can be either rectifying or ohmic. We're going to talk about what both of those things mean. So in a rectifying junction, the work function of the metal, phi m, is greater than the work function of the semiconductor material, phi sub s. We'll talk about what work function is in just a moment for those of you who are unaware. And in an ohmic metal semiconductor junction, the opposite case is true. The work function of the semiconductor is greater than the work function of the metal. Now, the derivations and stuff that I'm going to use today to explain how things are doing or how things are behaving is based on connecting a metal to an N-type semiconductor material. So you can form a rectifying junction or an ohmic junction using metals and N-type semiconductors. You can do rectifying and ohmic using a metal and a P-type semiconductor. So it is not as simple as, oh, if it's one type of semiconductor material hooked to a metal, it's this. And if it's the other type of semiconductor material hooked to a metal, it's that. Unfortunately, it's not that simple. It is all related to the work functions. Okay. So let's look at a rectifying junction first. So let's say that I draw the energy band structure of a metal and an energy band structure of a semiconductor, all right? So for the metal, let's say that this is my Fermi level. I'm going to call it EFM. You guys remember what Fermi level means? Did you guys learn what Fermi level means in 334? Okay, right. So we should observe that for a metal, all of the states below the Fermi level are occupied. So they have electrons. The distance between the Fermi level and what's called the vacuum level is the work function. So the work function of a solid material is really just the amount of energy required to move an electron from the Fermi energy level to vacuum outside the material. So it's effectively how much energy it takes to completely disassociate an electron from that material so that it is no longer interacting whatsoever It is completely outside, free, and in a vacuum above the surface of the material. So in a metal, you guys hopefully recall, there is no energy band gap. There's no difference between the conduction band and the valence band. They actually overlap. So we're not going to have an EC and a EV for our metal. It's just full up to the Fermi level, and then this whole region represents a crap ton of empty energy levels. For our semiconductor material, and I'm just going to do a generic N-type semiconductor. Since it's going to be an N-type material, it should have some electrons in the conduction band, which is what those black dots represent. The distance between the edge of the conduction band and the vacuum level is the electron affinity chi. For an intrinsic semiconductor, the Fermi level occurs at exactly 1/2 of the band gap. This is our valence band, completely, or not completely, but pretty dang close to completely full of electrons. Like I said, intrinsic semiconductor, our Fermi level would be at 1/2 of the band gap, but because we have an N-type material, that's going to push our Fermi energy level closer to the edge of the conduction band. And so let's call this dashed line EFN for the Fermi level of the N-type material. And the distance between the vacuum level and the Fermi level in the semiconductor is the work function of the semiconductor, defined in the exact same way, the amount of energy required to move an electron from the Fermi level to vacuum outside. So these are what the energy bands look like for a metal and for an N-type semiconductor when they're far away from each other so that there's no interactions or anything like that, okay? So we are going to consider the formation of our metal semiconductor junction as what happens when we move these guys close to each other and they fuse and stuff happen, and it happens forming a single device, all right? So if I move these guys close together, here's E, F, M, and let's see, I made that guy 4 tall. Here is EC. Here's EFN. Here is EV. These regions are full. And then here I have electrons. So this is what the instant of contact is going to look like, okay? So I have roughly ND electrons in the conduction band of my N-type material, and they see a whole bunch of empty energy states in the middle that are at a lower value. So electrons from the semiconductor material are going to want to move into the metal and occupy those lower energy states. Now, this isn't diffusion. And the reason why I say that is, let's say that the metal on the left-hand side were copper. Okay. So for every copper atom in our crystal, it's going to contribute, or it's going to have one free electron, right? And it has a density of electrons of somewhere on the order of, I think it's 8 times 10 to the 22 electrons per cubic centimeter. Okay. The density of states of silicon, so the number of silicon atoms per cubic centimeter, is 5 times 10 to the 22, right? So that's not like an overwhelmingly huge amount of electrons. The difference there is we're going to have just ND, the impurities are contributing these guys right here, right? So best case scenario, this is something on the order of 10 to the 18-ish electrons. So from a concentration gradient standpoint, there are significantly more electrons in the metal than there are free electrons in the semiconductor material. So it's not diffusion that's driving things. It's not drift that's driving that electron movement either, because there's no applied field or anything. It is literally just the fact that there are empty energy states at a lower energy level, and so the electrons want to go to there. All right, so it's not carrier drift, it's not carrier diffusion, it is purely driven by the fact that there are empty energy states here. All right, now what is going to happen is these electrons move to the metal, thereby positive charge starts to accumulate in the semiconductor side, because those donor atoms are literally giving up an electron. They're moving to the other side of the junction. And negative charge is going to accumulate in the metal. So we are going to have a depletion region. Okay. The depletion region is only going to extend into the semiconductor material. Okay. So let's just say, for the sake of argument, it extends to this point here. I'm going to call this W naught, meaning it's the width of the depletion region once equilibrium has been reached. We'll talk about that equilibrium constraint in just a moment. So as these electrons from the conduction band of the semiconductor material move over to the metal, we start seeing more and more positive charge accumulated on the semiconductor side of the junction, more and more negative charge accumulating on the metal side of the junction. And obviously this is going to give rise to a barrier potential, an electric field, and all that kind of good stuff, just like we observed in our PN junctions, except that, as I mentioned a moment ago, it turns out that the width of the depletion region is going to extend only into the semiconductor material, because it's the material that's actually resistive, right? So the side, just like the side that was less doped had a larger portion of the depletion region, it's because it was less doped, it was more resistive. Well, the metal has almost an infinitely large resistance, or it's almost a perfect resistance, right? So we should see that this depletion region extends only here. So what's going to happen is that an electric field is going to be established that is going to cause the bands of the semiconductor material to bend, okay? And they are going to bend until equilibrium is reached. And the constraint for equilibrium being reached is the Fermi level of the semiconductor material is at the exact same value as the Fermi level of the metal. So if I can draw what's going to happen, we should see something like this. The metal is going to be unchanged. All right, so here's our Fermi energy level for the metal. For the semiconductor side, this is going to be EFN. And away from the junction, it's going to have the exact same structure. So here's EC. Let me try to make my pictures the same. Here's E sub V. And our bands are going to bend in the direction, or up in the direction of the electric field, right? So if we have positive charge on the left-hand side, or excuse me, on the right-hand side of the junction, and negative charge on the right-hand side of the junction, we should see that our levels bend up, like so. All of them are going to bend by literally the exact same amount. Like so. And the amount that the bands have shifted is our built-in potential. So Q times V naught will be phi M minus phi S. So what has happened here is that now the electrons in, yes, we absolutely have the depletion region, and the depletion region is effectively the only place where the band is bent. You're 100% correct. We absolutely still have the depletion region. The depletion region doesn't really fully form until we've reached equilibrium. All right. So these electrons here in the conduction band of the semiconductor now see a barrier of V naught preventing them from moving over. So they need extra energy to get over this hump and get into the metal. So our barrier potential is doing effectively the exact same thing as it did in a PN junction. It is reinforcing the equilibrium state by allowing electrons to not move across that junction. All right. Now, there's actually a second barrier in this system. I'm going to call this guy phi B. Phi B is what's known as the Schottky barrier height. Its value is phi M minus the electron affinity, and it represents a barrier that electrons in the metal must overcome to get into the conduction band of the semiconductor. So we have these two different barriers in our system. Our built-in potential prevents electrons in the conduction band from moving into the metal. Our Schottky barrier prevents electrons in the metal from moving over into the semiconductor. So we're at equilibrium, where there is no electron movement from one side or the other. And so the total current flowing through the device should now be 0, right? So we have an equilibrium condition, similar but different to what we observed in PN junctions. Andrew. Yes, Chi. Yeah. All right, so so let's throw some math at you guys here real quick. And this is effectively based on the fact that this is a one-sided junction. So at equilibrium, the width of our depletion region is twice epsilon s, where I'm saying explicitly, so one thing that we do have to pay attention to here in our semiconductor junctions, or our semiconductor junctions, it was all one material, which is doped 2 different types. We have 2 different materials here, so I'm explicitly stating that the width of the depletion region depends on the permittivity of the semiconductor material. It has nothing to do with the permittivity of the metal, all right? So twice epsilon s V naught divided by Q times ND, all of the 1/2 power is the width of our junction. Again, excuse me, the width of our depletion region, which again extends only into the semiconductor side of the material. And since we have stored charge, we have a depletion capacitance. Yes.
So when we started the problem, you mentioned it was a N-type semiconductor. If it was a P-type, would it be Na?
Absolutely. Yeah. It's the dopant concentration. Yep. So CJ naught will be Q epsilon sub S A squared times the dopant concentration divided by twice V naught all to the 1/2 power, square root of the whole thing. And that's just gotten literally by saying that this is a parallel plate capacitor and the plates are separated by a distance of W naught. Okay. All right, so I'm not going to go into nearly as much detail about what happens when we bias things. We're just going to talk about things qualitatively here. All right. So what happens to this band structure if I forward bias this junction, meaning that I apply a positive polarity portion of the voltage here and a negative polarity portion of the voltage on the semiconductor side? So what happened in a PN junction when we applied a forward bias voltage? What happened to the barrier potential? Pardon? It got smaller, exactly right. So in an energy band structure like this, all that's going to mean is that everything is going to shift up. And so effectively, when we put a positive polarity voltage, the Fermi level of the semiconductor moves up by Q times the amount of applied voltage. So this guy is going to shift up, which means the barrier that is preventing electrons from moving from the conduction band to the metal gets smaller. So it doesn't take as much energy for them to make it over the gap, and we should see current start to flow. Some portion of that will be to diffusion. Some portion of that will be to what's called thermionic emission. And some portion of that will be due to tunneling. I am fully aware that you guys probably don't know what all 3 of those things are. That's perfectly okay. Thermionic emission is how incandescent light bulbs work, or electron guns and things like that. You heat it up and electrons start firing off. That's all that means. So we're going to have a reasonably large amount of current due to electrons moving from the conduction band over to the metal, or excuse me, electrons moving from the semiconductor material over to the metal because the potential, the barrier potential that's seen by those electrons is reduced. If we reverse bias this thing, or actually before we do that, does the Schottky barrier change? Not at all. Okay. So the difference, or so the potential barrier seen by electrons trying to move from the metal to the semiconductor is still just as big. Okay. So that application of a bias voltage, all of that voltage drop occurs in the depletion region, which is why we only see the semiconductor side move, because the depletion region is only on the semiconductor side. Right? So it's still just as hard to make electrons move from the metal into the semiconductor, but it's easier to make electrons move from the semiconductor to the metal. When we reverse bias this guy, we're bringing these energy levels down. We are making it more difficult to move electrons from the semiconductor to the metal while keeping the difficulty of moving electrons from the metal to the semiconductor, keeping it the same. Okay. So what we will observe then is that under bias, we will have a current density Jn, in this case, because it's only due to electron movement, of Q, which is the elementary charge, V, which is the velocity of electrons. And so this velocity really represents contributions of diffusion, thermionic emission, and tunneling, times NC, the effective density of states in the conduction band of the semiconductor material, multiplied by the exponential of negative Q times the Schottky barrier height divided by KBT. There's going to be more to this equation in a second, but I want to talk about this part right here. This term, the exponential of negative Q phi b over KBT, is the probability of electrons moving from the metal into the conduction band of the semiconductor. So it's playing the role of the reverse bias saturation current density that we saw in PN junctions. Then we're going to multiply that by the probability of electrons going the other way. So it behaves exactly like a PN junction with just slightly different parameters. So EXP Q V bias over KBT. This whole thing minus 1. So that when V bias is 0, this whole bit here equals 0 and no current flows through the device. And then that first big chunk, we're going to call JS, which is the reverse bias saturation current density for our rectifying junction, so that we can say Jn is equal to Js multiplied by the exponential of Q V bias over KBT minus 1, which should look exactly like the behavior of our PN junction. And it will have effectively a very, very similar looking IV characteristic curve, where As the bias voltage gets bigger, we see an exponential growth in the current. As bias voltage gets more and more negative, this guy just goes to JS in the opposite direction. Andrew. So this is, you can't really dope a metal per se, like they didn't realize so I think I follow your question. Just wondering why this was first try. I think it was a limitation of the fabrication process at the time. And so by that, I mean, putting metal on a semiconductor is pretty easy. Because if you have a semiconductor material and then you heat metal up, it's called sputtering, and it just forms crystals on top of the semiconductor material. So that does, like, effectively you heat the metal up so much that it vaporizes, and then it just lays a blanket of metallic particles over everything. So that's how you like chrome plate crap and all that kind of stuff. And those processes have been around for, I think, well over 100 years at this point. Whereas our understanding of semiconductor materials and how to process them and how to and all that kind of stuff didn't arise until, I want to say, our first kind of inklings of what was going on was in the 20s and something like that, and really understanding how to do things didn't happen until the 50s and 60s, where the technology became available to do things like ion implantation and all that kind of stuff, so that we could take a semiconductor material of one type, because we grew it that way, which is a very, I want to call it a simple process, simple in comparison as to how things are doped. And then we figured out a way to make, to switch that P-type material to N-type or N-type material to P-type through a compensation doping scheme. Because we can't grow semiconductor that has both. We can only grow it one way, and then we post-process it to make it to make specific regions the other type. Right? Whereas this is we grow the crystal, the semiconductor crystal, we heat up metal, and it sticks to it, call it a day. So the fabrication process steps involved are much, much easier. All right, so any questions about our rectifying junction? Okay, rectifying junction is effectively just a slightly different way to get the PN junction type behavior, right? So this is a Schottky diode. S, so this is important. There is Schottky and there is Shockley, and they both had things to do with diodes. So the metal semiconductor junction is Schottky, S-C-H-O-T-T-K-Y. I think England, but I'm not sure. And then Shockley and Bardeen and a couple other guys, they were engineers for what wound up becoming Intel. So they were American, and they were working on integrated circuits. So they took this work by Schottky and expanded it significantly. Maybe they did. Actually, I think they did. And then I don't know, I'm getting foggy on my semiconductor history. I apologize.
We should know this. I had a physics professor that preached about it, and we had like 3 lessons in a row about just the history of semiconductors class.
I find it super interesting, but I'm also a huge nerd. So like that's the kind of stuff that I watch on, you know, Netflix and Discovery Plus and all that kind of stuff to put my wife to sleep and keep me up half the night. So Anyway, that's neither here nor there. All right, so we're all reasonably okay with this because the behavior is extraordinarily similar to what we've seen for our PN junctions. So now let's deal with ohmic junctions. All right, so we're going to do the exact same thing. We're going to start with energy band diagrams. Key difference here is that the work function of the semiconductor needs to be greater than the work function of the metal. So this is my conduction band edge. This is my EFN. So this is going to be N-type material again. I'm trying to draw my semiconductor part literally identically. Oh, actually, that should go further because what I just drew was simply the electron affinity. And then here's my valence band. And so just to exaggerate this, here's my metal on this side. And it should be very easy to see now that the work function of the metal is significantly smaller than the work function of the semiconductor material. Phi m is much less than phi sub s. So when we move these guys close together and they fuse, forming a single device, it should look something like this. F M. Here's E C. E F N. E V. Sorry, somebody was calling me. And here are all my free electrons for conduction in the conduction band of the semiconductor material. So metal and N-type semi. All right, so this time we have a metal with lots of free electrons all the way up to the Fermi level. And it sees empty energy states in the conduction band of the semiconductor material. So we should see that electrons from the metal want to move to the semiconductor material. So as electrons move from the metal is going to get a positive charge. And the semiconductor material is going to get a negative charge. So instead of having a depletion region, we are going to have an accumulation region where we have excess charge carriers. right? So instead of literally extracting electrons from our dopants and moving them over to the metal side, occupying all those empty energy states, and getting a depletion region that is devoid of charge carriers, we are now moving electrons from the metal, and they're pooling and forming an excess carrier concentration in the semiconductor, giving us an accumulation region. So we have a region of space where there are more charge carriers than we would expect. All right. So as more and more electrons move from the metal to the semiconductor, we're going to establish an electric field, and we are going to see that the bands bend in the direction of the field again. So we're going to see that these guys should move up, and equilibrium will occur when the Fermi level of the semiconductor meets the Fermi level of the metal. So let me try to draw this real quick. Here's our metal. Here is EFN, EFM, and away from the junction again, we should see that our semiconductor material just looks like its normal structure. So here's EC, here's EV, but now we should see that in the accumulation region, we have our bands bending up. So that's going to look something like this. And this is our new barrier height. Q V naught is equal phi s minus phi m. And this is our Schottky barrier height, which is now negative. So when we get to this state, we are at equilibrium, right? And lest I forget, our conduction band still has electrons. So what happens when we bias this guy? Well, when we forward bias it, we're moving the semiconductor band structure up, right? And effectively, that just is giving these electrons more and more energy, making it more and more likely that they'll kind of roll downhill and wind up in the metal material. So for forward bias, for our ohmic junction, we see that conduction band electrons move into the metal. When we reverse bias this guy, we're bringing these guys down. And the electrons in the metal will see a small barrier height that they have to overcome to move into the semiconductor. So we don't have rectification like we observed last time. Effectively, current can flow both directions in this guy. So for forward bias, electrons move from the semiconductor to the metal easily. Reverse bias, electrons move from the metal to the semiconductor easily. And so instead of having that exponential current voltage relationship, we have a linear current voltage relationship, which means this is effectively a resistor. It's a resistor whose resistance value depends on the doping concentration of the semiconductor material. So the more heavily we dope the semiconductor material, the higher its conductivity and the less resistive it is. So the Schottky junction, or the rectifying junction, is a one-way valve for current flow, which is really what all diodes do. If you bias it one way, current flows very easily. If you bias it the other way, effectively no current flows, or very, very little amounts of current flow. For this guy, we have a linear IV relationship related entirely to the conductivity of the semiconductor material side, okay, which is exactly what we want in a lot of applications, right? If we wound up, anytime we put semiconductors and metals together, if we always got rectifying contacts, that would make a lot of different things completely useless, because it would mean that we could only ever apply our signal with a particular polarity and get anything out of it. So, Mr. Granger. A Schottky, the barrier level is 0? No, it can't. I guess mathematically it could be, if you were able to find a metallic alloy that had a work function that was exactly the same as the electron affinity as the semiconductor material you're fusing it with. But the probability of that, like, so that wouldn't be just, I'm going to hook aluminum up to silicon. It would be, I need some weird, crazy alloy specifically engineered to give me a Schottky barrier height of 0, which I don't think anybody's figured out yet. Pardon?
I bet it'll work if we just cool something after 0.
Actually, probably not. The reason why I say that is because these Fermi energy levels are literally defined at absolute 0, right? And the electron affinity and all that kind of stuff, I believe, are as well. So that doesn't actually help anything, because everything that we know about is based on a mathematical model of how things behave at 0. And then we just say temperature makes it more likely that stuff happens. So, I mean, maybe, but maybe not. I don't think you'll ever find one where they're exactly the same height, because that's not how probability works. You know what I mean? Like, for them to be literally identical doesn't happen. So anyway, so we have diode-like characteristics or rectifying characteristics when the work function of the metal is greater than the work function of the semiconductor. And then we have a simple linear current voltage characteristic when the work function of the semiconductor is larger than the work function of the metal. Again, we derived everything using an N-type semiconductor. There is nothing stopping us from doing this with metal and P-type semiconductors whatsoever. I just wanted to be consistent so that you wouldn't think you could only do one type of junction with one semiconductor and the other type of junction with the other semiconductor. So that's enough out of me for today.